A very warm welcome to all of you to this second edition of our webinar series of Notions of India with a focus on shaping the collective future. First off, I'd like to introduce to you Mr. Manish Jaiswal from Tata Steel Tubes Strategic Business Unit. Manish is the head of marketing for construction infrastructure, industrial and projects business of Tata Steel Tubes. He has 15 years of experience in various Tata Group companies. He has graduated as a mechanical engineer from the National Institute of Technology, Allahabad, and he's also an alum of the Tata Administrative Services, TAS, which is Tata Group's premier leadership program. In his current role, Manish is driving the marketing and customer relationship programs for the B2B of Tata Tubes, with a focus on construction and projects business. So over to you, Manish.
Thanks, Sanjana. Good evening to everyone who has joined this webinar. At the outset, on behalf of Tata Steel, I really hope and wish that all of you are safe and taking all precautions to keep yourselves and your near and dear ones safe in these testing times. At Tata Steel, our endeavor has always been to develop best-in-class products for our customers through collaboration. The construction and infrastructure segment is a very strategic segment, and Tata Steel remains invested in continuously developing and offering value-added sustainable products and solutions for our customers and the industry. Tata Structura is the first branded steel hollow section in the country, and it was launched as part of Tata Steel's long-term commitment to equip the architect, engineering, and the consultant fraternity with a new age and contemporary construction product. Over the years, it has transformed the construction landscape in India, giving wings to the imagination of architects and designers, and has enabled complex aesthetic designs become reality. It is a very versatile product and finds application across construction segments, infrastructure projects in airports, railway stations, metros, housing and commercial segment, large stadiums and sports arenas, industrial sheds, warehouse, and so on. In our quest to develop sustainable products for the construction industry, Tata Structura introduced the 355 grade hollow section, which is now a global benchmark in construction. And with an unmatched product range up to 400 hollow sections, we are giving new sustainable and quicker alternatives to traditional RCC construction in the country. Back in 2007, Tata Structura had commissioned a nationwide design competition, Notions of India, and had specifically asked the architects and designers to use hollow sections in creating a symbol. The competition had received tremendous response across the country, and it culminated in the construction of the Charkha in Mumbai's Cross Maidan. In the recent past also, Tata Structura has commissioned several iconic structures such as the Rath in Bhubaneswar and the Diamond Pavilion in Jamshedpur, all created with the hollow sections Tata Structura. Now in this year, Tata Structura has again launched another edition of this design competition, this time on a much larger and global scale, to create an iconic symbol that articulates the essence and glorious potential of India. It is an opportunity for the architects, designers, and engineers to revisit, reimagine, and recreate a nation's heightened ambitions. Not limiting itself to just a competition of ideas, Tata Steel has chosen to have the winning symbols of this competition erected and installed in public spaces across select cities in India. To inspire the best architects, engineers, and innovators before they begin the design process, we have launched a series of curated webinars called by Anjana, where we have invited very prominent influencers in the architecture fraternity from across the world to speak to you all. The last webinar we had conducted focused on the cutting edge usage of AI in architecture, and today's session is titled Designing with Mathematics, and our speaker is Mr. Joseph Choma. I hope that you enjoyed today's session and it inspires and helps you in your participation in the competition. Thank you.
As we rev up to celebrate India's 75th anniversary of independence, to bring alive the legacy of Tata Steel, Tata Structura launches its initiative, Notions of India. A seminal competition to celebrate India's journey and Tata Structura's mission to give the shape of things to come. A shape that will capture India in all its diversity, its enigma, which powers its extraordinary capability to metamorphose as we steamroll into the future such that it can stand tall while meeting the aspirations of its people. Notions of India, a design competition that brings fruition to an idea. It is a quest for an iconic, timeless symbol using steel hollow sections that will amaze and inspire. This is a call-out to our engineers, our architects, designers who are not restricted by size, our nation builders who will shape the future of the nation. Who will it be? Who will give the shape of things to come?
As Manish mentioned, we have launched this curated webinar series to inspire the best architects, engineers, and innovators. I'm delighted to see so many of you have connected today. Our topic today is designing with mathematics, and our speaker is Joseph Choma. We bring you nothing short of the best. Joseph is an award-winning designer whose interests lie at the intersection of mathematics, folding, structure, materials, and architecture. He is invested in the advancement of design pedagogy through computational thinking. He's the author of 3 books, Morphing, A Guide to Mathematical Transformation for Architects and Designers. Second is The Etude for Architects. And the third is Philosophy of Dumbness. So let's begin without further ado. I hope you all enjoyed today's session. Please feel free to ask questions during the course of the webinar. All the questions will be compiled and answered post the presentation. So over to you, Joseph.
Okay. Thank you so much for the introduction. All right, well, thank you again for having me today. I wish I could be there in person, but unfortunately, these are the circumstances we live. And a few years ago, I was in Mumbai, and I absolutely loved it there. And I can't wait to have another trip there in the near future. And again, seeing the video of Notions of India, and it's an absolutely inspiring competition that's being run. And I can't wait to see what some of the results are and the outcomes of this competition are. And I hope today I can provide just a tiny insight into a particular way of looking at the world and an approach to design, and hopefully it is of some value to some of you. A little about myself. So I am the founder and director of the Design Topology Lab. I'm also an associate professor of architecture at Clemson University, where I direct the Masters of Science in Advanced Architectural Manufacturing. And I essentially completed studies at the Massachusetts Institute of Technology in Design Computation. My research, somewhere in between mathematics, structure, and folding. Today, and I've done a lot of work in particular with foldable structures and materials, but today I'm going to specifically focus on mathematics. And I'm not going to be focusing on it in an engineering mindset, but more so in a very simple but poetic mindset of how it can be used as a design tool, but also how through the framework of this talk, you can also have a series of ideological frameworks or ideas to help you possibly move forward. Art does not reproduce what we see, rather, it makes us see. Paul Klee. When I think of this quote, I think about, in particular, the first time I had gone to Chicago, and I saw this project, Cloud Gate by Mr. Kapoor. I was there with my father, and I didn't know what to expect in Chicago. And then when we arrived at this place, I was totally mesmerized. And my most vivid memory is of this piece. First, I found myself walking up to it and engaging it and admiring my own reflection. Then, as I started to step back further, I found out that I also was amazed at the way in which it reflected the entire city of Chicago and transformed my perception of that place. After engaging it directly with myself, I decided to sit down at a bench and watch people for a while. And it was just extraordinary. I found that people not only, there was almost like a rhythmic dance to the way in which they engaged with it. They would move back and forth, and again, some dialogue with this kind of gaze. And so many people would come, and they would stay there for quite some time. It wasn't like they were there just for one moment. And then when you're underneath this thing, this is the kind of view you get. And I can't think of a better piece than this that would resonate with that quote by Paul Klee. Artists don't make objects. Artists make mythologies. Anish Kapoor. I think this is really an interesting quote, where this in some ways this talk, I'm going to be showing you a lot of shapes with math. But through those shapes of math, hopefully there's something deeper than just the mathematics. So if you want to, you can have a kind of a crash course on how you design with math at a technical point of view. If not, you can kind of forget all the technicalities of the mathematics and the equations and just look at the substance of it. And again, what are some of the maybe lessons that I'm trying to convey today? But in particular for Anish Kapoor, when I related to the Cloud Gate project, I think it's also about not revealing everything. And we don't know, part of it is the form. We don't know exactly how it was generated or if there's symbolism to it or not. We can speculate, and everyone can kind of inject their own vision. But also, the means and method of construction in this case is also delicately concealed. So the steel structure is somehow, or the steel skeleton is somehow cladded, but we don't see it. And as a result, the object that seems almost scaleless is magical. And so today, in some of that spirit, I'm going to be talking a lot about geometry, shapes, abstractions, which can be constructed out of steel, but I won't necessarily reveal the means and methods of how that detailing would occur. But it nonetheless is definitely a design decision. The way in which a problem is decomposed imposes fundamental constraints on the way in which people attempt to solve that problem. Rodney Brooks. So if I ask you to make a cube with a sheet of paper, you might put 6 squares together or cut a cruciform shape and fold it, and create a cube like this, a cube with discrete sides and edges. Well, if I gave you a ball of clay and I asked you to make a cube, you might compress it in multiple directions, yielding a cube like this, a cube with rounded corners. So depending on which tool or medium is utilized will influence the set of possible results. This also relates to an idea of instrumentation, or how we record something. In particular, while we're designing and we're doing iterations, we oftentimes record it through the act of making a drawing or rendering or model. This is a photograph by Andreas Feininger of a helicopter moving. When I look at this photograph, and also when I think about a helicopter moving, I think I know what a helicopter moving is like. But when it's recorded in this way with a long exposure photograph, my understanding of it transforms. For me, this is no longer about the helicopter or the movement, but it's a drawing. It's a wireframe drawing that allows me to look at the inside and the outside simultaneously, almost like an X-ray. This kind of representational abstraction is something I'm really interested in. So throughout most of this presentation, this will be the means in which I present shapes of mathematics. Now, also for instrumentation, it sometimes also relates to ideas of emulation. So if someone was to try to make a duplicate of a famous work of art, we would call that a copy or an emulation, or you could call it an instrumentation, literally recording it. However, this particular artist is adding additional rules or constraints. It's one continuous line with a brush pen, and as the pressure of that brush pen changes, the thickness or the line weight of that line also changes. And so here, by actually adding additional rules or constraints, you open up to new possibilities. And throughout the work you'll see, I utilize mathematics as a very specific constraint to yield opportunities that would not be possible with any other tool. That said, math, well, why am I into math? Why are we doing this today? Well, oftentimes when we operate in the computer and we're clicking buttons in a software, we're operating within somewhat of a black box. I click a button, but I don't really know what's under that button. I don't know what the DNA is behind it. So if I click on an icon to draw a sphere and I draw a radius, I have a sphere. But it's essentially a dumb object. I can't manipulate the smaller DNA of that shape. Well, when you go to something like mathematics, the degrees of freedom starts to change. Literally, the equation is the DNA for that shape. It's a one-to-one relationship. As the equation changes, the shape changes. In many ways, it operates like a transparent tool once you understand how to use it. I'm going to begin with a circle, possibly the most humble shape out there, but yet one of the most powerful. And it's one of these shapes that goes unnoticed, unrecognized, but in reality, it's embedded in much of the mathematical DNA of the world in which we live. So here's a circle, and here's a simple parametric equation for that circle. So we have a cosine, and we have a sine. That's all we have. But again, through this cosine and sine, we're able to define this geometry. When we look at a geometry like this, now we have a cylinder, and once again, that cosine and sine is recognizable within the equation. And in the z coordinates, we have a v, which is essentially allowing this geometry to extrude. So again, x and y is the grid on the ground, z is the direction up on this image, and essentially the v is allowing it to extrude vertically up according from 0 to pi. And then on another one, here we're looking at a helix, or a curve that's rotating around as it's going vertically up. If we were to look at this curve in top view, we would see a perfect circle. And in many ways, this one is also wrapping itself around the cylinder we saw before. But in this case, since there is no v, there is only a u parameter, all we have is a curve. So where previously in the z coordinates we had v, we now have u, which is just defining, essentially asking that curve to incrementally move upward. And you can see as I divide that u, this thing starts to shrink until it's back to a circle. Here's another similar shape. This is a helicoid. In other words, a spiraling ramp. And once again, we can see the cosine u, sine u, and the x and y. And once again, that means from the top view, we have an inscribed circle. And with this, we can also change the frequency of that, such that we're starting to change the number of them that we see. Then we also have things like a cone, or in this case, like a barrel vault. And once again, now the cosine u and sine u is in the y and z axis. Or here, where we have an undulating barrel, once again, the circle is inscribed in this geometry. And I could go on and on with many shapes that start to work with a very simple circle. But now let's try to see how, by understanding where we can, if we can identify a circle within an equation, how can we use that to design? So we're going to start with a dome. And we're going to look at a dome, and we're going to apply a very, very simple transformation. Just one transformation. And in many ways, this is almost like what Joseph Albers would say, minimum means maximum effect. How far can we push just one transformation? In other words, just one tool. But if we can calibrate that tool precisely, maybe we can do something extraordinary with it. The secret, I think, of the future is not doing too much. All architects have the tendency to do too much. Try on. And I really love this quote because, again, it gets to the essence of what can we do with the least amount possible. So we'll start with the circle again. And now I'm going to take that circle. And again, we're looking at the cosine u, sine u. And now we're looking at it in relationship to this, a dome. And when we look at this dome, we see here's a cosine u, sine u. So there's a circle. Here's a cosine b, sine b. There's another circle. And here's another cosine b, sine b. So we have a third circle. So a dome is just literally an interpolation between three circles. Now, granted, those circles are half circles because it's going from 0 to pi instead of 0 to 2 pi, as we can see at the top of the constraints. But essentially, that's all it is. It's just an interpolation of, again, of these three circles. And now that we know that there's three circles, we can start to understand if we change the shape of that circle, we can insert it into any one of these three locations to transform this three-dimensional boundary. So again, we go back to the circle. And now, by adding a function of cosine and adding a function of sine, what we are doing is we're doing something which I call translating. We're placing a higher frequency wave inside of a lower frequency. Or as Paul Klee would say, a curve inscribing itself. And if you notice, it says cosine 2u divided by 2. The reason there's a divided by 2 is that that's essentially creating a discrete edge or a discrete point. If that number was not 2, but was 3, so 2u divided by 3, we would get a rounded edge. And if that was 2u divided by 1, we would get a loop at that zone. So again, already the tool is starting to become calibrated. And we can see here when we have 3, or here where we have a frequency of 4, and then here with a frequency of 5. Now I can take this and literally all of the x, all of the y, to define what was once a circle, but now place it with this geometry. And now this is the dome we get. Suddenly we have a dome where it's been textured, but textured with semi-plastic curvature. And here we have cosine u plus cosine 5u, and same with one below. But if we change those pluses to minuses, essentially a minus and a minus, or a negative and a negative, still makes positive curvature. Two negatives make a positive. And so here we get a different kind of geometry that's similar to the previous one in the nature of it being symplastic, but a bit different in the way its periodic nature is expressed. And for me, when I look at a geometry like that, I don't just see a shape. I see something that has the illusion of being an inflatable structure. And it reminds me of these soap bubbles by Friado. And it's fascinating to me that something so simple, so dumb in reality, if you think about it, I mean, there's not much there, is able to generate something that normally would be generated through a very complex physics-based engine. and it would be normally quite difficult to simulate. And again, this is not a simulation. This is just a mathematical definition. So we'll continue with the circle again and see what else we can do. So now, if I make one of them positive and one of them negative, we get negative curvature. And so now you can see those arcs are pointing inward instead of outward. And here's the frequency of 4, and with the frequency of 5. Now I can take this geometry and once again apply it to the dome, which yields one like this. And when I look at a geometry like this starts to look like a tensile fabric structure almost. It looks like something in tension. It almost looks like there's ribs that are present. But again, it's not generated with physics. This is just literally inscribing one curve onto the three-dimensional shape of the dome. And then here you can see that if I switch the positive and the negative, with the plus and the minus, we get a different shape. But once again, we're still getting something that's a saddle-like geometry that's being essentially mapped around that of a dome. And once again, this reminds me of the soap bubbles by Friato. And to me, I start to think about this almost like materializing math, where the mathematics starts to almost have a material, but also I, as an individual, can start to manipulate the math and the equations as though it is a material. It starts to have something tangible to it. And so here you can see an animation of a dome transforming into these synclastic and anticlastic shapes, or those that are negative curvature or positive curvature, or those that look like they're inflatable or look like they're in tension. And this, to me, there's a real intense beauty and elegance in the simplicity, the purity of the geometry. And so maybe we don't have to do too much in order to make something that has a powerful impact. And for me, again, in my personal biased opinion, these forms and geometries are powerful because you can almost feel gravity, physics embedded within them. And you can almost still read the pure geometry of the dome when you look at them. And so just as one more example related to this, here are a series of 2D curves in a taxonomy. And then here are those curves applied to a dome in one of the dimensions. And again, if I go back and forth, if you look at one of them and you look here, you'll be able to see how they're applied. And this is a very architectural way of working. It's almost like working in section or elevation and then three-dimensionally. But it's done with very simple math. The next one we're going to look at is a spiral. And I call this seeing beyond. So here's a spiral. And when we look at a spiral, what's inside of it? Once again, cosine u, sine u. Within the mathematical DNA is once again a circle. It's just a circle that's kind of been pulled apart and wraps around. And if I change the frequency of that circle, you can see it gets much denser. Or rather, still it's a spiral, but it's a denser nested spiral. But it's still a spiral. That's all it is. We made a spiral, we see a spiral, that's what we see, and that's what it literally is. But something funny happens when you start to apply texturing to it. In particular, once we start to increase the frequency of the cosine and the sine, we start to get strange patterns that start to look like moire patterns, like we see here and here. The only difference from typical moire patterns is this is only one curve. It is only one spiraling curve. It is not the superposition of multiple curves or two spirals on top of each other. This is only one. So literally, one curve is giving this visual illusion. And some of these may seem predictable, like in here, you can see some symmetry relationships. But as we move through this, we can start to see ones that start to have directionality or biaxial symmetry. And then we get other ones that start to look very different. Suddenly, when I look at this one, I see something that looks like it's rippling. I don't see a spiral anymore. But it is a spiral. But I don't see it. I see something else. And so there's a certain power in making something that goes beyond what it once was into something else and being open to that transformation. And again, you can look at the equation and see how subtle the changes are. And one like this for me is quite interesting because the way in which it starts to break some of the symmetry. Or this one here. And again, this is just one curve in space. And it's a two-dimensional curve, not three-dimensional. And now when I get to a drawing like this, what do we see? Probably see all sorts of things. It's moved way beyond where we started. But we started with something very simple. And through precise calibration, we were able to get extraordinary perceptual effects. Again, minimum means maximum effect. But also, as Paul Valery would say, to see is to forget the name of the thing one sees. I think that drawing on the previous page does start to make us see and forget what we're looking at. It moves beyond dictionary definitions of what a spiral is. Now I'm going to get into a torus, or a donut. And for this one, we're going to start to look at it from, I'm calling it exuberance. But it's also going to look at it through a lens of some irrationality and not being afraid to try things. But at the same time, still calibrating the tool or technique that you're using. And so here is looking at a torus or a donut from an elevation-like perspective. And when we break down the equation, so at first, if someone wants to look at this equation, you might say it looks really complex. But now that you know what to look for, we can break it down. So cosine B, sine B, we know what that is. That's a circle. Sine U, cosine U, we know what that is. That's also a circle. Sine U, cosine U, that's another circle. So once again, a torus or a donut is just an interpolation of three circles. And if you think about it, it makes a lot of sense. And then you see we have this 1.5 that's being added to the sine U. And that right there is what is essentially making it not a sphere, but making it a donut. It's essentially controlling that radius. So if we take that 1.5 and we increase it, the radius increases. If we take that 2 and we decrease it to 1, then it starts to kiss at the centroid. And if we remove the 1, we're back to the sphere. Next, we're going to look at that U and V. I haven't talked too much about that yet, but that's essentially the parameters that control the extent of a shape. So we have 0 to 2 pi and 0 to 2 pi. If I change it to be half a pi to 2 pi, you can see in the u parameter how it's been cut. So this is a cutting operation. And the same can be done with the v parameter, but once again, it's cut in the other direction. Now we're back to the torus again. And now we're applying twisting. So having u plus v together essentially plots the geometry along a diagonal trajectory. So incrementally moving along a diagonal. And in order for us to see that diagonal, we also have to cut the shape and see how that edge condition has changed compared to the way it was previously cut. And then here, the transformations which we've been doing before, we apply texturing. So we have a frequency of 30 placed inside of a frequency of 1. And you can see we get this jitter-like texture all along the surface of that geometry. Well, if I change that texturing transformation from 30 to 2, you can see how that calibration drastically changes the geometry. It feels much more like a global deformation or undulation rather than a ripple along the surface. So same transformation, different calibration. How do you calibrate the tools you're working with? And then here again, taking the donut or the torus, and by placing them inside of functions of sine, we're able to flatten it on all sides into the boundary of the cube. So this would be called flattening. So how do we take some of these basic transformations? Now I've introduced you to some additional transformations, such as cutting, texturing, flattening, twisting. So instead of just looking at one, now we're looking at a few more. What can we do with this torus? What can we make? So we first do some texturing. Then we do some twisting. After twisting, we apply flattening just in the Z. And then we apply cutting as a means to enter. And this is a moment where one could be satisfied, or one could say, I want to just try something, see what happens, try something else. I want to challenge what I've done, even though I might be satisfied with the results. And so if I start to place a 2 in front of that V, we start to get a double twist. Now that we have a double twist, we start to get into ideas of duality, contested symmetry, two halves that are competing with one another for hierarchy. And it becomes a very different kind of thing than the previous one, which has a very clear singular directionality associated with it. Here is what the single twist looks like. And here is what the double twist looks like. And although this geometry wasn't generated with the ideas of symbolism, one could argue that there is, or one could embed ideas of symbolism into it. From certain vanishing points, we see an infinity symbol. It's a loop. It's a closed loop, suggesting togetherness and unity. It's dynamic but static. It has energy. It feels like it's dancing. It's not just a platonic solid, like just a dome or just a donut. And again, the idea of two halves or two coming together, many people could start to read and interpret their own symbolism. And so therefore geometry in general, and through its abstraction, can yield many different effects, even beyond the author's intention. This is looking up the single twist, and then this one is looking up that double twist. And one of the things I really like about this particular view is we get these ripples along the surface. And for me, these ripples along the surface are like singularities, which allow our eye to trace a three-dimensional curve in space, almost like a three-dimensional drawing. So similar to the way in which Anish Kapoor's project, the reflection becomes the dominating dialogue between the individual. In this case, I think the eye would be attached to those curves and trying to trace them in space. There are two kinds of scientific revolutions, those driven by new concepts and those driven by new tools. In the last 500 years, we have had 5 major concept-driven revolutions. During the same period, there have been about 20 tool-driven revolutions. Freeman Dyson. Now, I don't know about you, but the idea of a concept-driven or tool-driven reality, for me, they go back and forth all the time. They're always in flux. It's never just one or the other. They're usually more blurred than distinct. If you have an idea for this competition, you should start making something to test it. Drawings, models, digital files, whatever. Find a way to look at it, interrogate it. And then through the testing, by making, you'll likely find new criteria to bring the project further and challenge your initial concept. On the other hand, if you don't have an idea, what do? If you don't know what to do something. I believe you don't need a genius idea to start. You can start anywhere. Just by writing an algorithm, folding a piece of paper, using wooden dowels, anything. Doing a sketch on a piece of paper with pencil, folding paper, anything can generate ideas. If you're consciously looking at what you're making and reflecting on it, you can use it as a generative tool and identify new opportunities that you did not premeditate or imagine before. And that's the real beauty of design, is that we're open to the unexpected. And we have a conversation with the means and mediums that we're working with at our fingertips. And so I encourage all of you, again, if you don't know what to do, just start doing something. And that's what I have for you for today. Thank you so much.
Joseph?
Yes?
Yeah, you want to look at the questions?
Sorry, I'm just trying to go through all the questions. They're moving quickly on the screen.
Yeah, the first one is, how did you get into mathematics as a designer?
Okay, that's a great question. So when I was an undergraduate student, I was really interested in just digital tools in general. And so I very quickly started to try any tool that was out there. I learned how to do creative coding and write algorithms, and whatever was the most advanced parametric model at the time, I tried to learn. And literally, I was more interested in, as an undergraduate student, in the tools I was using, more so than the actual project itself, or the brief of the project. And when I went to graduate studies, and I went to Massachusetts Institute of Technology, I thought, okay, I'm going to study computer science while I'm here, and I'm going to look at what I can to essentially really become an expert at software, per se, and to develop new tools for myself and for the discipline of architecture. I quite quickly realized that even computer science and programming has what's called a hierarchical heuristic. In other words, it's still very much structured in a hierarchical way. And so I realized that maybe I have to get into something even more fundamental. So I started to look at mathematics. In particular, I came across someone named Joseph Fourier. In the 1800s, Joseph Fourier tried to prove that every signal or shape could be made with sine and cosine. And he got close to proving that everything could be done, but not quite. But again, this was a big influence on signal processing. And this blew my mind. But I also found mathematics bizarre, because it's like, the discourse of mathematics, or the discipline, because they keep writing proofs. So I want to prove that everything can be made. Or I want to, and when I think about a designer, what good is a proof that says we can make every design? That doesn't tell us how to make every design. So I became really interested in math as a transparent tool, and as a way to kind of critique many digital tools that many people were jumping on and using, but didn't really realize how the engine was driving the projects. but I also started to become interested in just the beauty of the geometry. And so instead of starting with super crazy equations, I found myself starting with simple known shapes like cylinders and spheres, and looking at how do I transform one of those. And that was through a trial and error process. But I also started to, again, just fall in love with geometry and the purity of it and how we can control it very precisely. And that kind of eventually that led me to go on to look at other things like materials and structure in relationship to geometry. But yeah, that's a little bit about how I got into math as a designer.
Okay, many of the participants want to know which software you are using to create such wonderful shapes.
Yeah, so the software I'm using dominantly used is Rhinoceros, but within Rhinoceros, I essentially write my own code within that program. And you can do it with RhinoScript, Python, Grasshopper. It doesn't really matter which one. And but yeah, that's usually the software of choice for me. But I do write my own code within it, so it's not a automatically built-in plugin or button within the software. I'm creating my own tool within that tool. And yeah, that's the program we use dominantly.
Yeah, so one more question is, do we always consider golden ratio while designing or crafting new geometrical shapes?
I don't think we always do. I think I think there's always some kind of proportional relationship. But the functions I'm using, they're periodic functions, so they have a certain kind of repetition or change in repetition over time. And so there's again a certain kind of quality to them. But yeah, I wouldn't say it's specific to just one ratio, like the golden ratio per se.
What should be the first steps for architects to learn coding? How can they learn coding? How can they do something with shapes?
That's a great question. So the way in which I learned it was in a very, and same thing with math, was in a very non-traditional sense. So instead of reading math books, I just literally tried things out, trial and error. And at first I had no idea what I was doing. It was kind of more like, a monkey on a computer typing in things, and then whatever the computer pooped out, I looked at and I interrogated. But eventually I started realizing, oh wow, if I place this inside of a function of sine, the shape flattens. Let me write that down. And so actually through my tacit play with the tool and the equation, I started to learn how to control math by literally just recording what these transformations did without knowing necessarily all the technical mathematics behind it. And then a lot of that knowledge was then recorded in my book Morphing, Back to Mathematical Transformations. And as far as the coding part of it is concerned, I started out by learning coding by just looking at other codes and then trying to see what happens when I change something within the code. Does the code not run? How does the code change? What happens if I take some code from one and some code from another? I combine them. So again, I learned it in a very non-traditional way, but quite quickly understood what a for loop does and things of that nature, an if statement. And and so I think one could go through a normal computer science class, but you can also, there's so much resources out there and there's so much information that's shared, you can also just try things. I frequently give workshops on designing with mathematics for free, and so I'm always happy to share knowledge with other people.
Yeah, could you speak a bit on origami architecture or folding architecture, as it is also related to mathematics?
Yeah, absolutely. So I didn't show anything with folding in this particular talk. I decided to keep it just focused on using trigonometric functions. But I am doing a lot of work with mathematics and computational geometry with folding. In particular, a lot of the work I'm interested in right now with folding is with curve crease folding. And I'm really interested in how with curve crease folding we create what's called a bistable structure. In other words, a curve that or a crease that pops into place. And when it does that, it's basically like what you could think of as controlled buckling. And normally buckling you think might be bad. So then if you look at my hands, if this thing pops like this, that might be bad. But when you're using buckling to your advantage in a very controlled way to make the structure stronger, it can be a really beautiful thing to work with. And so there is a certain back and forth I'm doing with the mathematics and understanding in relationship to buckling. Some of that is also getting to other things like physics, because sometimes you do have to also look at material constraints. And then there's also some work I'm doing with computational geometry, where I'm trying to understand how to interpolate from a smooth surface to a folded geometry. And I've been working on that as well, and looking at the Gaussian curvature and the mapping and kind of the input geometries. It's a little hard to describe all with words without kind of showing visuals, but those are some of the things that are works in progress for me.
Yeah. One question is, the shape on the opening page of your presentation reminds me of the iconic Capitol Gate building at Abu Dhabi, which holds the world record for maximum leaning angle with such height at 500 feet. My question is, can you find geometric equation for that structure too? How to incorporate stresses on these geometries and see the effect?
That's a great question. So I guess not specific to exactly that building, but in my morphing book, the beginning chapters, the way that book is structured, I first show these are fundamental transformations. These are how you combine different transformations in different order. The order in which you combine them makes a difference. Then these are combining parts of shapes with equations. But then after I had that my understanding, or I designed an understanding of math, I then used it as a way to design a new understanding of architecture for myself. And so what I did as part of that was I started looking at buildings and trying to understand what is the most basic topological ancestor of that building. So if you imagine like Shigeru Ban and Friato's Hanover Pavilion, it was essentially a tunnel arch geometry it's undulating. And that one started out as a cylinder that's turned on its side, or a barrel vault. And then I was able to, again, undulate it to be exactly the same geometry as that building. But then after doing that, I was able to make a whole bunch of other variations beyond what that original architect imagined, because I was using a different tool to get to that same geometric output. So I guess to answer the question is, yeah, you can definitely, and I did it also for the ramp inside of the Mercedes-Benz Museum, by UN Studio, and many other buildings, several other buildings. But I think if you're doing it through pure just sine, cosine, trigonometric functions, that's just the geometry. That geometry is not taking into consideration loads or forces. It's more, there's no gravity in that. But you could take that geometry and then further apply it through other kind of computational geometry to have structure as part of the constraints of it, and do some form finding exercises with that as well. But they're kind of different frameworks, and there's advantages to both. I would say, form finding is different than form making. What I was showing today was mostly form making. It wasn't trying to optimize something to a very specific solution. It was much more like the sculpture play idea.
Yeah. What do you think is the interrelationship between form-based, computer-generated, and emotion-driven concepts?
That's a really good question too. Especially since many of you might have heard a talk on artificial intelligence before this one. So there's a lot of work done with AI right now in architecture, where they're using images and interpolating between images with machine learning, and then they're trying to take those two-dimensional images and turn them into three-dimensional artifacts. That's one kind of trajectory that some people are doing. The way in which I presented it here was that when I work with a three-dimensional geometry in the computer and I'm rotating around, I'm looking at it three-dimensionally. But a lot of times during that process, I'll stop, pause, and I'll make a drawing. Because sometimes when I make a drawing, like one of these wireframe drawings, its literal representational abstraction helps me generate new ideas. I might see something that's actually not there three-dimensionally, but it's an illusion, and then I say, oh wow, I actually want that to become real. How do I now do that with the math? So I think there's a real beauty in representational abstractions when you work with that. So I think there's a lot of value in stopping, pausing, recording it through a certain lens, and then allowing yourself to digest it further with your eyes.
Yeah. What is the difference between standard coding and visual coding?
I guess Standard coding is you're using a particular programming language, so there's a certain kind of linguistics associated with it. Like Python has a particular kind of heuristics and linguistics associated with how it's structured. While visual coding is more like things like Grasshopper, where there's built-in buttons that you're kind of drawing relationships to. So, I mean, one of them is literally you typing lines of code, and the other one is you creating relationships by dragging and connecting kind of prefixed functions together. So that's kind of the biggest difference, but fundamentally they're quite similar.
Yeah, Joseph, there are lots and lots of questions, but I think we don't have so much time right now. 1 second. Which algorithm should we follow while choosing a shape? And one more is, we saw examples of unity and togetherness. What would be the geometrical examples of diversity and differences?
That's a tough question. I don't know. I don't know if I have an answer to that. And I don't know. I mean, maybe what it is also just about not having a premeditated answer, but just trying things, making things, reflecting on them, not trying to premeditate exactly what that geometry has to be for the symbolism that you're after, but just allowing the process to take you somewhere unexpected. And then as you're doing that, see if when something is starting to get closer to the evaluation criteria or the poetry that you're after. And yeah, I don't know. I mean, I think that's kind of what it is. It's really, I don't think one can have just a single answer for a question like that. But it's kind of question where you yourself has to kind of explore it, and maybe to kind of elaborate on it a little bit more. I think one of the things I was trying to say today is just form and geometry does play a role in how we perceive the world and how we read symbolisms and how we just visually see something that has kind of emotional effect on us. And I hope you all explore it and have fun with it. Don't try to overthink things. Just play. I would say do rigorous play. I think if you trust in the process of uncertainty, amazing things will happen.
Yeah, is there any link where we can find more about your work?
Yeah, so I think I will have my website, which is designtopology.com, is firmly under construction. I've been updating it, but you can always follow me on Instagram at Joseph Choma Design, and I frequently post on there, and you can follow me there. There's also a Facebook page, Design Topology Lab, and so you can, which I think it's just called Design Topology, so you can follow me there as well. And the website will probably be up and running within the next month or a month and a half or so. Yeah, it's a big change from my previous website, and a lot of new work and exciting work. Yeah, and I hope to see some of you in person in the near future. Again, I had such an amazing time last time I was in India, and I can't wait to come back again and share more knowledge and see what you're all doing.
Okay, Joseph, there are lots and lots of questions coming in, but I don't think we're out of time. So thanks a lot. I know it's the early morning over there in USA, but thanks for your time. And I think the audience has loved you. I'll share the remaining questions with you on email.
Great. And thank you again for the invitation. This is an amazing event that's being run. And yeah, and I'm just feel very fortunate to be able to share some knowledge with you today. And yeah, stay safe and well, and I look forward to seeing the results of the competition.